All right, by this time we've talked a lot about channels, we've talked a lot about the types of molecules that need help crossing the membrane. And remember again, if things are nonpolar, they'll get through the membrane pretty much on their own, especially if they're small. But if things are polar, especially large polar, or have any charge, then they need help. Right? And so we started talking about all of these different things. We even culminated with an idea of neuronal signaling in how channels and membrane gradients and so forth really relate to neuronal signaling. So hopefully you're comfortable with all of that by now. Now we're going to take a step backwards and we're going to talk a little bit more about transporters. And the reason I saved this kind of for last, this asynchronous part, is I think this is a little bit easier to understand without us being synchronous in class together, especially if you already understand the concept of channels and a lot of those transport across the membrane already. So the first thing I want you to think about is which of these lines corresponds to the movement of ions through a channel. So let's think about this for a second. This is the solute concentration difference. So this is important to think about. So this means if you have a high gradient, you're over here. If it's a no gradient at all, meaning the solute has the exact same concentration on both sides of the membrane, you would be over here. So as you move further to the right on the x-axis, you're creating a higher concentration gradient. So in other words, one side of the membrane is going to have a lot more of that molecule than the other side. Right? And then on the y-axis we have rate. And again, we're starting down here at 0, but this is a rate of solute movement across the membrane. So basically, if you have membrane, or if you have molecules that are being moved across the membrane, or moving across the membrane on their own maybe, depending on what the situation is, what's going to happen with the rate as you get more and more of that concentration gradient? And so within this, we have several line options. So we have the dotted line here, number 1. We have this guy here, number 2. This is line 3 with that drop, and then this is line 4. So which of these lines would correspond to movement of ions through a channel? See what you answer there. And then remember to kind of give a little bit of your rationale as well. All right, so let's talk about these together. The line here that would correspond to movement of ions through a channel would be number 1. All right, and so let's talk a little bit about why this is the case, and then we'll talk about why the others would not work. So first of all, we know that movement through a channel is very, very rapid. Right? So as long as you have a gradient, things are going to flow from high to low through that channel as long as it's the correct ion. Remember, channels are also very specific. So if we have a sodium channel that's opening and you have a very high gradient, right, a high difference of sodium concentration on one side to the other, sodium is going to flow through that channel very, very rapidly. And so we're going to have this really rapid rise in the rate of movement as soon as we have a gradient at all. Right? But why does it plateau out? Right? Why does that not keep going? Well, eventually you run out of channels. Right? Channels are limited in the membrane, and so even though those ions can flow very rapidly through them, those ions we know do not get through the membrane on their own. And so once every channel is open and the ions are flowing as fast as they can through there, even though that's really, really rapid, you come to a ceiling. Those ions cannot move across the membrane any faster anymore because there are no more channels to open up. So because movement of ions across the membrane is dependent on helpers, in this case channels, there is going to be a limit, an upper limit, because at some point the channels are working as fast as they possibly can. Right? So that actually is why number 4 here would not be the case. A hint is that number 4 is not moving things very rapidly across, but I don't even really have a scale here, so maybe this is extremely rapid. But the difference is that number 4 never reaches a plateau. And if you have something that needs help getting across the membrane, it's going to reach a plateau. Now, number 3 doesn't make sense because as you get a higher and higher concentration gradient, you have more and more potential energy. Right? Those things are going to want to move from high to low, even more so if the gradient is high, or if the gradient is big, I should say. And so therefore this wouldn't go down. So this is basically a backwards line, if you will. Now what about 2? 2 would work. It reaches a plateau. We have some pretty fast movement here. The reason 2 is not the answer is simply because it does not reach zero here. If you do not have a concentration gradient, it doesn't matter if your channel is open or not, you're not going to get a net movement of ions from one side to the other. Ions will still move across, right? So you'll still get an ion moving this way, but you'll get the same number of ions moving this way, and the net rate of solute movement, right, the rate of solute change across that membrane is not going to be zero. Or it would be zero, and therefore you're not going to have that high rate. So that's kind of the main reason number 2 would not be the case. In past, in face-to-face, people have argued that, well, there still is movement, right? Ions are still moving this way and moving that way, so you still have a rate, but you do not have a net rate, and so that's kind of where that is, even if that's a little tricky. All right, so let's jump to the next one. Assuming that number 1 now corresponds to the rate of movement through a channel, which of the lines to the left, all right, and they're mostly the same, but they've moved around a little bit, so pay attention to what they look like. So assuming that this one here, number 1, corresponds to the rate of movement through a channel, which corresponds to facilitated transport of glucose across the membrane, right? So glucose, relatively large, not way large, but still a large polar molecule that's larger than water, right? So which one of these would make the most sense there? Give me your answer and your reasoning, and then move on. All right, so I would argue here that the answer is number 2. Number 3 has the same issue that we had before when we had a straight line. If we know that glucose needs help to move across the membrane, it's large polar, it's not going to get across on its own, so it needs help. But it's going to move via a transporter rather than a channel because it's pretty big. If you had a channel that was big enough to allow glucose to flow through, that channel is going to be very hard to maintain its specificity. Because in order to open wide enough for glucose to get through, now even though we have all those aqueous shells and those cool things that we've learned about to maintain specificity, those ions are so much smaller, they're still probably going to get through. So when you get to something large like that, it needs a transporter rather than a channel. The aquaporin's water is really kind of the largest thing usually that flows through channels. Anything bigger needs a transporter. Now, transporters are going to be slower, and we'll talk about this in just a second. But transporters mean they still need help, so you're still going to reach a saturated level, a plateau, where all of those transporters are doing all that they can, and so it doesn't matter that you're getting more and more of a gradient, they just can't move across the membrane any faster because all of the transporters are already working at max capacity. Okay. This backwards line still doesn't make sense, and I'll explain why transporters are slower than channels, and so why it could not be number 1 equal to the speed of a channel. And then last question, which line corresponds to passive diffusion, right? So you have facilitated diffusion meaning it's still moving from high to low, but facilitated means it's using a protein or something to help it across the membrane. Passive diffusion, high to low, but it doesn't need help. So which line would correspond to that? Well, passive diffusion basically does not need help, and if you don't need help, you don't have an upper limit. So the bigger your gradient is, the faster things are going to move through. And so number 3 would correspond to that passive diffusion because we are not going to run out of helpers because passive diffusion doesn't require helpers. The more you have, the more chance you have of those things hitting the membrane with sufficient speed, with sufficient direction to basically make it through. All right, so let's go back to an earlier question. Why are transporters slower than channel proteins? So we know that you have facilitated diffusion, we know we have channels, and we know we have transporters. We know that both of those have that upper limit, right? I'm not going to talk about Vmax, Km, Michaelis-Menten, things like that. But we know they have a limit because they needed help to get across. But it's much slower than channels, but much faster, at least at lower concentration differences, much faster than simple diffusion. So faster than diffusion, diffusion was 3, facilitated transport 2, but slower than channels. And I do want to emphasize that unless we're talking about active transport, facilitated diffusion is still based on a concentration gradient. But facilitated diffusion basically means that you have a transmembrane protein that has to open to one side, It's going to bind, and then it's going to open to the other side. So here, on one side, your solute binds. That triggers a conformation change that opens it to the other side, and the solute is going to be released. Now, if you have a lot of solute on this side, high concentration and low concentration here, then when it's open to this side, you have a high chance of solute binding. And when it's open here, it's going to diffuse to where there's very little. And then that will trigger opening back up. So it still is only moving from high to low. If you didn't have a concentration gradient, it doesn't matter how many times this thing opens up and to one side or the other, you're still not going to get a net movement. But this is why it's much slower. Remember, a channel just opens and ions start flowing through. Now, it's specific, and there is very rapid interactions because the channel is mimicking the aqueous shell, but it just opens, tons flow through, and then it closes. Transporter has to open, bind, all right, so this binding pocket here is active kind of quaternary-like structure. You're going to have hydrogen bonding, you're going to have ionic bonding, you're going to have some type of interaction that holds it there. So that bonding takes a little bit of time, and then you need a full conformation change to open to the other side, and then you need release, and that's going to take time. It can still do it actually relatively rapidly. It's pretty amazing how fast these things can go, but it's going to be a lot slower than channels because you need that conformation change and you need to actively bind to the solute as opposed to just let it go through. All right, so types of transporters. They're basically based on two things: the number of molecules being transported. So you've got uniporters and symporters. Uniporters move one thing, symporters means it moves two different types of things. And then if you have a symporter, you can have direction. So you can have a uniporter where both things, all right, so in this case this is modeled by our circle molecule here and our triangle molecule here, both are moving in the same direction. That's a symporter, same. An antiporter is moving things in opposite directions. So here our circle solute is moving from out to in, and then our other solute here by this little cylinder is moving from in to out. Antiporter moving in opposite directions. All right. So we've actually seen a really important example of an antiporter already. Our sodium-potassium pump that restores the gradients in our neurons is an antiporter because it has to pump sodium back out and potassium back in. Both of those are moving from low to high to restore the gradient, so that takes energy, but they're moving in opposite directions. The sodium-potassium pump is a great example of an antiporter to restore the sodium and potassium gradients in neurons.